At the end of the last video, our computer looked like this. We could look at any address in memory. We just had nothing to look at, because there ain't no memory. If you're building along with us, this is what you'll have by the end of the video. Don't worry, you can make yours better than ours. We won't be offended. In this video, I'll be using 2 breadboards, one 62256 32K SRAM, one 74HC245, one 74HC32, one 74HC08, one 74HC123, 8 LEDs, one 8-way dip switch, one push button, one 1 nanofarad capacitor, one 10 nanofarad capacitor, 2 22K resistors, 10 1K resistors. Before we start making anything, let's have a look at the old simulator, shall we? So let's start as always by switching it on, then doing reset. Now in this video we're looking at the deposit function, and what that does is allows us to change the data that's being stored at a specific memory address. So in this case we're looking at memory address 0, and if we change one of these switches and then we press deposit, see it's placed that there. Then if we plug it back, and it's gone back to a 0. So if we go dud, 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 and now do it, we get a nice little pattern on there. So this allows us to program the computer, which is pretty useful for a computer really. A computer that you can't program, well, it's not really worth having, is it? So let's build it. Human man, make some room for the RAM. It rhymed. Ha. Human man, zoom in. Now make the display for the data bus. The Z80 has an 8-bit data bus, so we need 8 LEDs and 8 1K current limiting resistors for those LEDs. Come on human man, add the RAM! This is the RAM we're using, 62256 series. Now add power and ground, and if we look at the pin out, there he is. So this is the one we're looking at. Power is pin 28 and ground is pin 14. The RAM chip is a bit like the Z80. It looks scary because it's got loads of pins, but actually it's not that bad. So let's just start by looking at the data pins, which on the RAM chip are called I/O. So we've got I/O 0, 1, 2, all the way to 7, which form our 8 data lines. So all we need to do is just connect these 8 data lines to the 8 data lines on the Z80. Be careful when you're connecting up the data pins, because Mr. Zilog, for some reason, thought it would be a laugh to jumble up the data pins on the Z80. So make sure you connect all the data pins of the Z80 to their corresponding pins on the RAM chip. Otherwise, weird stuff will happen. Now let's connect up the address bus, which is the same process. A0 on the Z80 goes to A0 on the RAM, all the way up to A14. After connecting up power, ground, the data bus and the address bus, well, we're only left with these 3 pins. So we've got CS, that's the chip select, so that turns the chip on. We've got OE, which is output enable. When this line is active, the chip outputs data. Then we have WE, which is write enable, so we can write data to the chip. So let's start connecting these up. the output enable pin will connect that to the read pin on the Z80. So that's pin 21 on the Z80 is connected to pin 22 on the RAM. Next, we'll connect up the chip select, and we'll just connect that to the memory request line of the Z80 for now. The memory request line goes active when the Z80 wants to read or write data to memory. So we're connecting pin 19 of the Z80 to pin 20 of the RAM. And then lastly, we've got write enable, which we're just going to tie high for now. So we'll just put that to power. Now let's plug the Examine Next board back in and give it a try. Go on then, human man, switch it on. Whoa, quick human man, switch it off, switch it off! It's burning! Oh look, these wires have gone all melty. Check them chips, human man, might be one of them. No? Well, I wonder what it is then. Well, we took the RAM out, and it wasn't that, it was still doing it. And then, we had a look at these resistors. Now the human man, he was playing around, hardwiring opcodes onto the data bus. And he hadn't put one of the resistors back in ground, so there was one in power and one in ground. And if you got big long bits of metal, one in power and one in ground, and they touch, it's gonna short out. So, stick that back in ground, stick it back together, and now let's see if it works. Human man, I hate to have to tell you this, but we can't actually see what's going on. The LEDs, they're not on the screen. You'll have to refilm this bit. Oh, human man, look, the sun's come out. No one can see what's happening. Here, get that notebook over there. Yeah, hold that up. Oh, it's working. Well, it's not actually working. This is one of those happy situations where it looks like it's working properly, but it ain't. So let's figure out what's going on. Well, it's pretty simple what's happening here. The RAM chip, well, he's just bunging a random hodgepodge of ones and zeros on the data bus. So when we press the Examine Next button, the Z80, he's just reading in some random instruction. We don't even know what it does. We don't really want that, do we? So what we need to do is come up with a circuit that when we press the Examine Next button, it turns off the output of the RAM chip. And we can do that with just a single OR gate. All we need to do is OR the mem request line with the wait signal. So when either of these signals go high, then the RAM chip, well, it will stop putting stuff on the data bus, which is exactly what we want. So let's wire that up. So this is what we're going to be using for our OR gates. The 74HC32. And as you can see, it's got 4 separate OR gates. So let's stick that chip on the board. Now add power and ground, where power is pin 14 and ground is pin 7. So we're going to use this OR gate here, where the two inputs are pin 1 and pin 2 and the output is pin 3. So let's start by connecting up the mem request line to pin 2. Now let's connect the wait signal to pin 1. Now connect the output, pin 3, to the chip select pin on the RAM chip. Don't forget to connect all your unused inputs to power or ground. So that's pins 4, 5, 9, 10, 12 and 13. Come on, human man, plug that power supply back in. Let's test it. Look at that, it's only working. Whoa! Now let's actually build the deposit function. This is the circuit we'll be making. Let's just build it and go through how it works afterwards. It's more fun that way. So human man, like you normally do, start by adding power and ground. Now add the dip switch. Add the 74HC245 and connect power and ground, where power is pin 20 and ground is pin 10. Then connect up all the B lines to power. That's pins 11 to 18. Now tie the direction pin to ground because we want the direction to be B to A. Now connect all the A pins to this side of the dip switch. That's pins 2 to 9. And doesn't really matter which order you connect them in. This little circuit here lets us select any 8-bit value we want to write to RAM. So let's connect it up to the computer. Now let's make the deposit button so we can actually put whatever value is on these dip switches into memory. This is very similar to the debounce circuit we made in the last video, except that the Q output of mono 1 goes to the B input of mono 2 and the Q bar output of mono 1 goes to the right enable pin of the RAM chip, and the unused A input on mono 2 just goes to ground, and the Q bar output goes to the output enable pin of the 74HC245. This circuit is actually pretty simple. When we press the deposit button, this triggers mono 1, which activates the right enable pin on the RAM chip, so it'll write whatever data is on the bus into memory, and at the same time mono 1 triggers mono 2, which puts the data from the dip switches onto the data bus. It's important here that mono 2 be triggered for a longer time than mono 1. This is so the data on the bus is stable during the whole write cycle. The human man here, he thinks he's finished. He thinks he can test it. Have you spotted his mistake? Well, let's see how long it takes the human man to spot the mistake. There we go. He's found it. He forgot to connect up the data bus. So whenever he pressed the deposit button, it was just putting zeros on it. So connect the dip switch to the data bus. Switch it on, human man. Try it out. Oh, human man, we can hardly see it. Oh, even though we can't see it very well, it's actually working. Ooh. At the end of the last video, I did say we'd run a little program. But before we do that, we need to come up with a way of running the computer. So to do that, we need to make the wait signal go high. It wouldn't be any fun if I gave you all the answers, would it? So here's the signals we have, and underneath this purple blob, that's what you've got to fill in. Don't worry, I'll give you the answer in the next video. So this is our little test program. do nothing 4 times, and then go back to the start. I think you'll agree that it is a very, very exciting program. So, the human man is now going to put this on the computer. So, address 0, well, we put all zeros on the data bus. Address 1, we put all zeros on the data bus. Address 2, we put all zeros on the data bus. Address 3, you guessed it, all zeros on the data bus. And then at address 4, we're doing something different. We're putting C3 on the data bus. In binary, that's 1, 1, 0, 0, 0, 0, 1, 1. We haven't seen this before, have we? This is an unconditional jump instruction, and what it does is it takes the following 2 bytes and then sticks them on the program counter. So it jumps to any location in memory. At address 5, usual service has resumed. All zeros on the data bus. This forms the low byte of the program counter. And finally, at address 6, yep, all zeros on the data bus. And this is the high byte of the program counter. Let's run it! Well, isn't that exciting? It's slowly counting up. And then it goes back to the start. So there you go. Our little Pooty, he's growing up, and I think that'll do for this video, won't it? Next time, we'll make the run stop function.